All right, greetings students. So I put together this tutorial for folks who might need some additional support on how to do chemical quantity conversion. To get started, really what you need to do is you really need to own three facts. Those three ideas that are all equivalent to 1 mole are important or critical ideas for understanding this particular concept. So let's briefly talk about what those three quantities are equal to 1 mole. So we have what we call a particle amount. The challenge with particles is there's three different words that can sort of describe them. They're either called atoms, molecules, or formula units. It really doesn't matter which of those words that are used. There's always a quantity of 6.02 times 10 to the 23rd particles equal to 1 mole. So that fact needs to be owned or memorized. The next fact relates to the volume of any gas at what we call standard temperature and pressure. There's also a fixed quantity or number. There's 22.4 liters of any gas as long as the gas is at standard temperature and pressure. So that would be the quantity of gas volume equal to 1 mole. What complicates this for some is the idea of something called mass. So mass varies for individual chemicals because every chemical has its own identity based on its formula. So we have what's known as the molar mass. The molar mass of each chemical, I've laid out three examples here: carbon dioxide, water, and something called iron 3 oxide. The molar mass of each of these is based on the parts that contribute and the quantity of each element that contribute for a particular chemical. So carbon dioxide, when we consult the periodic table, adding up the mass of 1 carbon and 2 oxygen atoms. So if we go to a periodic table, what we can do is we can look at just the information that relates to iron. So if we look at, maybe we're looking at that iron 2 oxide, or iron 3 oxide, excuse me, 55.85 grams for every 1 iron, but since there were 2, I would multiply that by 2. Oxygen, right? Atomic mass of 16. So the particular chemical called iron 3 oxide requires 3 oxygens and 2 irons when we go back and look at the formula, right? Fe2O3 right here, right? Fe2O3. We add up the mass of 2 irons and 3 oxygens, we get 159.70 grams. So the chemical formula determines the molar mass of every chemical. And this is the quantity that varies depending on which chemical we talk about. Recall that particle amounts equal to 1 mole is always a fixed value, 6.02 times 10 to the 23rd. And gas volumes, as long as the gas is at standard temperature and pressure, that amount is always 22.4 liters. Okay, so let's go to work with a few examples of how to use a strategy. So we're going to take a look at a strategy that uses what we call proportion method, setting 2 fractions equal to one another and then solving for an unknown. So recall, these are the factors that would relate chemical quantity to the idea called mole. So these are the things we'd have to know before solving any problem. And then we would just become a reader. And as a reader, we read for a given quantity and read for a desired quantity. So the method that I have here, it says we start by making a first fraction equal of the given quantity over the desired quantity. So let's just read here real quick. How many moles? Well, that's a desired quantity of ammonia gas, or equivalent to 29.7 liters. That's our given quantity. So our given over our desired, our X, we use the units of measure in the fraction. That'll allow us to set up a proportion. So let's get to work with setting up the proportion. The given quantity, 29.7 liters, so we label it with liters, over the desired quantity. It says how many moles, so our X value is our unknown in a mole amount. Now, when we set the fraction on the right, what we're looking for are the quantities that are equal to 1 mole. So for liters, the quantity equal to 1 mole is always 22.4. So the labels liters have to match the top or the numerator, liters on the top on the left, liters on the top on the right. And the label mole has to match on the bottom. Anytime that the mole quantity is given in the left side of the fraction, we simply transfer over the quantity 1 mole. So if we see the word mole on the left side, we're just going to transfer over 1 mole on the right side every time. For any other quantity, we transfer the quantities equal to 1 mole, either 22.4 liters, 6.02 times 10 to the 23rd particles, or the molar mass in grams. Now we cross multiply, and then that allows us to set up an equation, 22.4 times X, and then 29.7 times 1, create an equation out of that. 29.4 times X is equal to 29.7 times 1. You'll solve for X by dividing each side by 22.4. And that will give you a quantity of 1.33 moles. You've just solved your first problem using proportion method. Let's take a look at a second given and desired example. So in this example, it is given a gram quantity, grams of the chemical called CH4. And what it wants is a volume quantity. What volume of methane? So we'll start by setting up our given in grams of CH4 over our desired X liters, because it asks for a volume. What volume? Remember the labels for the numerator and the denominator have to match. So where did I get 16.05 grams? Well, that's the quantity equal to 1 mole when we are dealing with a mass. Grams is a mass quantity. We need to recognize that. So 16.05 comes from adding up the mass of 1 carbon and 4 hydrogen using the periodic table. And what goes on the bottom then is the liter quantity equal to 1 mole. Notice the fraction on the right shows quantities equal to 1 mole. The molar mass in grams, 16.05, and the number of liters equal to 1 mole for any gas when we talk about its volume. Again, we cross multiply, 16.05 times X, 975 times 22.4. Right, what that would allow us to do then is to set up an equation, divide each side by 16.05, and we end up with X equals 1,361 liters. Given over desired, when we use this strategy, it always organizes us. An organized strategy is the best approach for a mole quantity conversion. Let's take a look at one final example. Now it asks about an atom quantity, and it gives us a volume quantity. So our given is a liter amount, 87.5 liters, and it asks about how many atoms. So our X is now going to be an atom quantity. And remember the fraction on the right, the labels match for both the numerator and the denominator, but what we put for the numbers are the quantities equal to 1 mole. There's always 22.4 liters of a gas equal to 1 mole, as long as it's at standard temperature and pressure. There's always 6.02 times 10 to the 23rd particles. In this case, the particles are just called atoms. We would cross multiply, turn it into an equation, right? 22.4x is equal to 87.5 times 6.02 times 10 to the 23rd. And then we would divide each side by 22.4. And we end up with a atom quantity, 2.35 times 10 to the 24th atoms. A very consistent strategy. So we start with a given quantity over an X desired quantity. And on the right side, we put the quantities equal to 1 mole. So in this case, since liters was given, 22.4 went on the top. Since, particles were desired, 6.02 times 10 to the 23rd went on the bottom. The fraction on the right are the quantities equal to 1 mole. So I hope you'll use this strategy or an equivalent strategy. This is just one strategy that can be used for solving mole quantity proportions. Until the next time, bid you well.